Hello, welcome to your second and last lesson in this unit. The application unit is really short because we spent that whole unit just learning our derivative rules. We're now just applying them. So our first lesson was last week on the rectilinear motion. Hopefully that worksheet went okay. And then today we'll look at related rates problems. Again, there's nothing new. We already know our derivative rules. So we're just applying them in a different way. So again, I really do think these are fun because now there's a reason why we learn things in math, especially in calculus. We'll take our derivative rules and just apply them. So it's all word problems, so they're a little bit fun. So first time through they may seem difficult. The math isn't hard. Like I said, it's equations we know, math we know, derivative rules we know, just putting them together in a way that's maybe a little bit different. So the hardest part is actually getting the initial equation and figuring out what do we have, what are we solving for. But once you get that in place, it gets a little bit easier. And the good news is after you do a few, there's only so many different types. So first time through, it may be a bit difficult, but you've done that in previous units, that once you kind of expose yourself to kind of the different types of word problems, you should start to recognize patterns and setups and trends. So today we'll just talk about generally related rate problems, what they are. Then we're going to solve 3 of them, and hopefully those 3 are enough to get you through your assignment. We only have 2 classes this week, and that's all we're doing this week. We'll do the notes today on related rates, and then today you'll do a textbook assignment. Then your next class this week, I have that worksheet with you. I think there's, I can't remember how many questions. Quite a few to practice with a worked out answer key. So if you do the textbook and the worksheet, like I said, first they might be a little bit difficult, but after your first time through, you're like, oh, I get it. I can see what the equation is. I can see what type of problem it is. And usually, traditionally, this is the halfway mark of the calculus course. When we link up with university, the midterm would cover everything from day 1, limits, derivatives, and usually related rates is the cutoff part. So congratulations, that means we are halfway through this course. Okay, so let's give this a try, related rate problems. So I haven't written out everything fully on the board to save me some space and time, but if you follow along in your notes, I do have it fully written out. So related rate problems. So yes, they are word problems. And they are problems where we figure out the rates of certain things. Pretty self-explanatory. So related rates just means that we have 2 variables. Sometimes it's more, but we have at least 2 variables that are related through some kind of equation. That's where we get the related part from. And then the variables themselves are changing with respect to time. So we start with our equation, and then as things change over time, we're just going to solve for a certain rate of one of our variables. That's kind of the simplest version of what related rates are. So we're not going to work through this fully, but just, I don't know if you can see the top of this. Okay, so let's just simply start with the volume of a cube, going way back to grade 10 math. Remember we did surface area, cubes of all those shapes. So the volume of a cube, the volume is S cubed, pretty simple. So if we just started with a cube, what if it expanded? So when the cube expands, then there's 2 things that change: the rates of the length and then the volume, right? So if it expands, that means that the lengths are changing, increasing, but as you increase the length or the sides of it, then the volume also change in response to that. So you have 2 things changing. So as the side changes, so does the volume. So when it expands, then both the side and the volume change with respect to time. WRT. Oh, that's not a bad thing. Okay, WRT with respect to time. Okay, so for this example, that's our starting equation. V equals S cubed, that's our equation. So when, I know for notation, we've used different versions of notations for derivatives. I think we've been using the S prime. We would have been using maybe S prime, V prime last unit. When we do related rates, this is the version that we use, ds over dt. The rates that the side is changing with respect to time. So the side changes with respect to time as it changes. So that's the notation we'll be using for these problems. That shouldn't be new to you. We haven't used it a lot, but you definitely have seen that. And then the side changes, so does the volume. So this is the rate at which the volume changes with respect to time. So those notations we'll be using in our problems. Okay, now for the next slide, still just looking at this simple example with a volume of a cube. So when the side increases, the volume increases as well. So what if we wanted to determine what is the rate at which the volume changes for this cube as the sides increase? Step 1, you need the starting equation, which we already had. The volume of a cube is S cubed. Then we go back and use all our derivative rules, some implicit differentiation, chain rule. We're gonna have to use product rule. But like I said, that should be pretty easy for you. I saw from your hand-ins that you know your derivative rules quite well, so that part shouldn't be that bad. Okay, so let's differentiate this equation. So V equals S cubed is our equation for volume of a cube. Then as it changes, so dV over dt, that's the rate at which the volume changes. Now, using a derivative rule, S cubed, the derivative of S cubed is 3S squared. That's really easy derivatives for us to do right now. But then you have to add at the end ds dt, right? You do the derivative and then the change of the side with respect to time. Okay, then it's pretty easy. So step one, you're going to get the basic equation. Step two, you will apply your derivative rules to get that. Then, ideally, you should have only one unknown variable, and then somehow, somewhere, the rest of the values are given to you. Sometimes directly, and sometimes you have to do a little extra math to get to there. But the rest isn't that bad. So if they give us the side length, and if we were given the rate at which the side changes, then we would just insert solve, and we easily could solve for the rate at which the volume is changing. We're not actually solving this. I didn't give you numbers, but just wanted to start with a very simple, easy equation just to kind of show you the overall concepts of related rates. Okay? So you first of all figure out how they're related, and then you solve for the rate. Simple enough? Well, let's keep going. So just a general steps before we go to our first one. So it's kind of hard to summarize how to apply it because every question is slightly different, but the same steps basically apply to every question. So step one, determine what are you given and what do you want to find. Sometimes that's easy to tell, sometimes that's not as easy as to tell. So step one, what are you given and what are they asking you to solve for? Step two, write an equation that relates the variables together in step one. Again, this is the fun part. The equation will not be given to you, and there's no formula sheet like there was in pre-cal. So they kind of expect you to know every kind of possible equation for things like volumes and areas that we've covered over the past. So hopefully that'll come back to you as we go through these examples. So figure out which equation you use that connects all these variables that you have in step one. Then step three, differentiate. This should be the easy step, right? The differentiation rules, we've been working with that for about a month. So once you figure out what your variables are and you have the right equation, steps 3, 4, 5 are pretty easy. You differentiate, then you substitute the values that you know, and if you've done everything correctly, you should just have one unknown value, and that's what you've solved for. So that's kind of the 5 steps that apply to everything. Unfortunately, this is the fun part. Steps 1 and 2 are fun because every question has different variables and different equations in different ways they are related. So here we go. We'll try 3 together today, and then you have all week to work on this topic. Okay. So example number 1. Maybe it might feel like a physics class when you see things like this. So I know all 3 of you are in physics as well, so hopefully it's not too bad to do. So like I said, I've written out the shorter version just to save us some time and space. But if you follow along, I have it fully written out in your notes. So we have a boat that's being pulled by a rope towards a dock, which is 7 feet above the water. If the rope is being pulled at a rate of 15 feet per minute, how fast is the boat moving through the water when there are 25 feet of rope out? Okay, there's a lot going on in that question. So like I said, the fun part is figuring out what am I given, what I want to solve, what's my equation. So very simply, I drew a diagram. So this is our boat, and this is the dock. And you can see that the diagram we have is a right angle triangle. That's going to be useful for us right away. We'll label it X, Y, Z. Technically, they didn't tell us what letters. You could do A, B, C, I guess. It doesn't matter. That wasn't given in class. So whatever letters you use, you can just use that to connect your work. So I use X, Y, Z, so that's why I'll have that in my equation. So in this question, what are we given? We are told that the rate at which the boat is being pulled in, so this is the boat being pulled into the dock. We know that rate. We know that dz over dt is 15 feet per minute. That was given in the question. And the question wants to know how fast is the boat moving. So we were given this is the rate we want. How fast is the boat being pulled in, or how fast is it moving through the water? So we want the rate at which it's moving in with respect to time. So we're given dz over dt. We want to solve dx over dt. And they do tell us the length of the rope is 25 feet. So we know that z is 25 feet. Okay, so that's the fun part. Like I said, this is kind of the hard part. Once you get this in place, the rest shouldn't be that bad. So we need an equation. So clearly it's a right angled triangle. So like I said, this isn't really calculus anymore. Just going back to Pythagoras' theorem, which we've been using for many years. So x squared plus y squared is z squared. Now in the question, y was a constant. So y is, oh, I think I put 49, but y is actually 7. Sorry, I was a step ahead. They tell us that the height of the dock is 7 feet above water. Yeah, sorry, that was 7. I was a step ahead. Okay, so now you can see where this is going. So that part never changes, right? The other two changes, right? The x and the z values, those change, but the height of the dock, that doesn't. So y is always 7. So when you insert and solve, sorry, that's where the 49 came from. So x squared plus 49 is equal to z squared. Okay, but we need x. Why? Again, well, I just know we need x because I've done questions like this before. If you didn't know you needed x, you might try and differentiate, and then you'd realize later on you do need x. So the way that you do these, or the steps doesn't matter, but I just know that we're going to need x. Trust me on this one. So if we need to solve for x, again, the rest of this is pretty easy math for all of you at this point. So we use Pythagoras' theorem to set up an expression or equation for x. So x is equal to z squared minus 49. Now, the point that we're solving for, we said that we want to know the rate at which it's moving when we had 25 feet of rope out. And again, hopefully all my math is correct. So 25 squared minus 49 should be 576. Okay, so now we're ready to solve the question. So we are going back to this question, x squared plus 49 equals z squared. Now we can differentiate with respect to time. So x squared, the derivative of x squared is 2x, but remember we are differentiating with respect to time. The derivative of 49, a constant, is just 0. So you can put the plus 0 or you can just leave it. The derivative of z squared is 2z, and then remember it's our implicit differentiation. So last unit we would have put x prime, z prime. Now we're just using this notation with our related rates problems. Okay, now does anyone remember what we are asking to solve in the question? We are trying to solve for this, dx over dt. That's the question solving for. But before we solve, we can clean this up a little bit, right? We can divide both sides by 2. So our equation now is x dx over dt, z dz over dt. We have 1, 2, 3, 4 variables, but we actually know 3 of those 4 numbers. We can insert, substitute, and then solve. So we know in the question, we just solved for x. So if you didn't realize why was I solving for x, if you didn't see that, you could have done this step. Then at this point, you have to say, oh, I'm stuck, I need x. Then you can go back and do the step that I already did. The order that you do it doesn't matter. So we already know from the previous screen that x is 576. We don't know what dx over dt is. That's the rate at which the boat is moving in the water. That's what we're trying to solve for. We do know that z is 25. That was given in the question. And dz over dt, the rate at which it's moving, is 15. So that was given in the question. That we solved for. That's our unknown. I'm running out of room. So to solve for this, this is pretty easy math. You just do 25 times 15 divided by root 76. So it should be 375 divided by square root of 576. So because I have amazing mental math skills, I don't need a calculator. I know that that is 15.625. Remember, that is feet per minute. So yes, you do need to include units as well. Okay, that is related rates. Do you see why they're so fun now? If you ever heard people talking about calculus, you probably have heard about related rates and optimization problems. They're kind of like the trig unit of grade 12 pre-cal. It's kind of challenging, right? The math is easy, but just to get the setup, that's hard. But like I said, the more you do, the more you practice, it comes out naturally. Okay, 2 more examples. So in this example, we have a 6-foot tall man is walking away from a lamppost that's 24 feet high at a rate of 4 feet per second. What rate is the length and his shadow increasing? So in this diagram, this is our lamppost here. It's a height of 24. This is our 6-foot man. and I've just labeled that x and y. So again, what are we given? So we are given x dx. We know that Shiv, you're roughly 6 feet tall, is walking away from the lamp post at a rate of 4 feet per second. And we want to know what's the rate at which his shadow is moving. So this would be his shadow. When he walks away, what's the rate at which his shadow moves? Okay, so again, the fun part, we need to know an equation. The equations are not given to us. We do not get formula sheets. We need to figure it out. Again, they're assuming that you have done every single word problem in your life and you've remembered everything, so you should be able to see these are similar triangles. So from our triangle, 24 is to x plus y as 6 is to y. So we did do some similar triangles work back in pre-calc. So just using similar triangles, and then now you can just cross multiply. So 24y equals 6x plus 6y. We can simplify to get 18y is equal to 6x. So that is our starting equation. Okay, that's not too bad. This is a little bit easier than that last one. Now we don't have to do a side equation to get another variable. We can use our equation, and now we differentiate with respect to time. So the derivative of 18y is just 18, but instead of a y prime, we're going to put dy over dt. The derivative of 6x is just 6, but instead of putting an x prime, dx over dt. So this one's quite a bit shorter and easier than last time. So again, we are solving for dy over dt. That's what we're looking for, the rate at which Shiv's shadow is changing as he walks from the lamppost. In the question, 6 is 6, and they did tell us that dx over dt is 4. He was walking away at a rate of 4 feet per second. So again, we have 24 over 18. So we can simplify, that is 4 over 3, and don't forget your unit, feet per second. So quite a bit shorter and easier than that first one. Okay, and our third and final one we'll do is a cylindrical can. Again, if you read it out, a cylindrical can is being heated with its height increasing at a rate of 0.01 centimeters per minute and the diameter at a rate of 0.005 centimeters per minute. What rate is the volume increasing when the can has a diameter of 15 centimeters and a height of 20 centimeters? Okay, there's a lot of numbers in that question. I drew a can. You don't need to. I just like having visuals. So what did they give us? They told us the rate at which the height is changing. The height changes as a rate of 0.01 centimeters per minute. The diameter, I used a big D, not a small d for diameter like we normally do, because the d's are kind of representing our derivatives. So the diameter is changing at a rate of 0.005 centimeters per minute. That's all given in the question. We want what's the rate at which the volume changes. And they tell us that the diameter is 15 and the height is 20 centimeters. Okay, so what's our formula? So yes, they do expect that you remember what the volume formula is for a cylindrical can. Remember way back in grade 10 pre-cal, we did that unit on surface area and volume. We had that sheet with all those formulas. In calculus, they expect you to just know formulas like that off the top of your head. So that's not that bad. And the only thing to notice, though, this equation has radius, but we never talked about radius. Everything in our example talked about diameter. So we have to change radius into diameters. We know that radius is diameter divided by 2. We better know that. You wouldn't have made it to calculus if you didn't know how to go from radius to diameter, so that's easy. So to get our formula, we have to change our radius into diameter. Oh, and the school has a mistake. That's not a 3, that's a 2. After I gave that big long speech about knowing your formulas. Okay, pi r squared h. Yes, that's the correct formula for volume of a cylindrical can. So not a 3, but a 2. There we go. So now we fill that in. We can clean it up a little bit. D squared is d squared. 2 squared is 4. So that is our formula. So just to clean it up a bit, pi over 4 d squared h. So that is our starting formula. Okay, so our next and final step, we can differentiate with respect to time. If the screen will change, differentiate with respect to time. So our starting equation was v equals pi over 4 d squared h. Okay, now this is fun. We get to apply the product rule when we differentiate, but you're all good at that. I saw that in your hand in. So the rate at which the volume changes, pi over 4 is a constant, so I'm just going to pull it out. So we just have to apply the product rule to d squared h. So remember, it's fg prime plus f prime g. So we keep the f the same. The derivative of h is just dh over dt. Then the derivative of f, our first one, would be 2d times, oh, now I'm using some small d's and big D's for diameter. I should have made all my d's big just to be consistent. Sorry about that. So you know that big D represents diameter. The small d's we'll keep for our derivatives. Okay, just to be consistent. And then h we don't do, right? So that's our product rule. Okay, so if I've done everything correctly, and hopefully I have, it looks long and tedious, but we now know, all these values on the right-hand side, so we just have to fill it in. So we were told that the diameter is 15. We told the rate at which the diameter, or which the height changes, was 0.01. 2 is just 2. We were told in the question that the diameter is 15. We were told the rate at which the diameter changes is 0.005, and we were told that the height is 20. Okay, so if you've done all that math correctly, it's a lot of numbers, but it's easy. You just insert and solve. We should get 5. Oh, even our pen is quitting on us. We should get 5 point. We're almost done hanging, guys. 5.25 pi over 4, and the unit is centimeters cubed per minute. Okay, so yes, you've hit the point in the course of related rates. They're not that bad. Like I said, first time through, it seems a little overwhelming, but just as you practice, I'm giving you lots of practice questions and all week to work on this, that once you do enough of them, you start to see patterns and routines. Okay, good luck. Have fun this week with related rates.